Welcome to NPTEL. Myself Dr. Jayanto Das from Department of Metallurgical and Materials Engineering, IIT Kharagpur. I will be teaching you advanced materials and processes. This week we are discussing about some advanced functional alloys, and we have already discussed in the last class about the Heusler type of compounds or alloys for various type of functional application. Today we will continue this discussion and we will try to look at how shape memory effect can be achieved by application of a magnetic field. So, let us try to look at these magnetic shape memory alloys. This is also an advanced alloys and understanding is being developed day by day, and there are many different system has been evolved with very interesting properties of shape memory effect. Now, these alloys are often called as the ferromagnetic shape memory alloys, because we also need to interact with a magnetic field. So, these should be ferromagnetic material, and these are basically a subgroup of shape memory alloys, and it shows a very large reversible strain upon the application of the magnetic field. What I want to mean in very short, there are two phenomena that are very much important to understand the phase changes or magnetic domain change by the application of an external magnetic field. So, these two effects is we can get magnetically induced reorientation and distribution of twin martensite variant. During the discussion of shape memory effect, we have learned about that shape memory effects are produced during because of the martensite, which has minimum two different types of variants. One was called as twin 1, another one is the twin 2. Okay. So, these two variant, one of them grow in expense to other due to the application of stress, but in this case here one of such a twin that grows in expense to the other one upon application of a magnetic field. So, very similar type of effect. In one hand, the for the conventional shape memory alloy it was stress induced. In this case today what we are discussing, it is actually the magnetic field induced. Now, the redistribution of such twin martensite variant without bringing any structural change. So, this is called as MIR. This is magnetically induced reorientation or redistribution of the twin variants in a martensite. Now, let us have a look at these MIR effect, magnetically induced reorientation effect, where there is no structural change. Here structural change means like martensite austenite type of structural change is not present. MIR effect shows that we have twins in the martensite, and this is actually one type of twin. This is one type of twin and this is the magnetic domain. Okay. And we have another type twin, this is another one, okay, like that, opposite in nature, and these are the twin boundaries. So, this is the twin type 2 and this is twin type 1. Now, we apply a magnetic field and one of the type of twin that aligned due to along the direction of the magnetic field. So, they are all aligned now, and one type of twin is growing in expense to the other type of variant, twin variant. Ultimately, by increasing this magnetic field to a much larger value, we have aligned all the twins to a particular direction, or we have grown all these twin of one type, and also the magnetic domains are oriented in the same direction. So, this is a typical ferromagnetic type of behavior. However, we will get such a behavior of this large reversible strain, means if I withdraw this magnetic field, then again we can get back the strain that is generated. So, here this is, let us say, the strain axis, we have generated this amount of strain, right. So, this is something very interesting. Now, the second type of magnetic induced phase transition in this ferromagnetic shape memory alloy is that we apply magnetic field and we induce a structural transformation, let us say from martensite to austenite. Okay. And because of that, we call this effect as MIM, means magnetically induced martensitic to austenitic transformation. So, in this case, since a structural phase transformation is involved, we can take very similar type of structures here, and we apply actually we apply actually some magnetic field. Now, here we have a austenite phase where the magnetic domains are aligned anti-parallel, and so, and these are the old phase front and this is the twin boundary. Upon application of the magnetic field, the yellow color region is the austenite, and so we produce austenite from martensites, or martensite transform into austenite. At the same time, we align the domain, magnetic domain, along the direction of the applied field. Now, austenite phase cover the entire martensite upon application of higher magnetic field, and also the domains are also aligned with increasing H, and this is a typical example of MIM, or magnetically induced structural phase transformation from martensite to austenite. This is also a very interesting phenomena in case of a ferromagnetic shape memory alloys. So, we now need to recapitulate whatever we have discussed about nickel titanium, you may recall, and in that case we have told that we need a special type of lattice relationship, so that the structural transformation could be reversible. Okay. So, like a structure of B19 dash, which is a martensitic structure, and let us say the B2 structure, which is the austenite structure, and those structures should be reversibly transformation should occur. Definitely we also need a martensitic transformation in that case. So, let us say we have a martensitic transformation and we need some special type of relationship, so that we can get 100% shape recovery. So, this is let us say a typical shape memory effect, okay, or SME. And so, if we combine these two different effect, one is the special lattice relationship and martensitic transformation, this is a domain which should cover basically the typical shape memory alloys like nickel titanium. Now, in other case, a material which can show ferromagnetic behavior, which are ferromagnet, and in case of iron nickel there is a martensitic transformation. So, the field which occupied by these two is basically like iron nickel one. Now, if we combine these three different, all three different type of behavior, then the combined region shows basically the ferromagnetic shape memory alloy, means these are ferromagnet, there is a austenite martensite phase transition, as well as they have some special relationship of the lattice, so that it exhibit a shape memory effect. And like iron platinum, iron palladium, the Heusler compound, and you may recall these are the half Heusler compound that we have discussed in the last class. So, this is just a conceptual position of different alloy system which has both martensite, ferromagnetic behavior and a special lattice relationship group, so that we achieve this shape memory effect. and the overlap domain of the ferromagnetic shape memory alloy with the other ferromagnetics and shape memory alloys. Now, there are two major possible actuation mechanism that are possible in this case of ferromagnetic shape memory alloy. I mean, where do we use these alloys actually? The first one is to utilize the shift of the transformation temperature by an external magnetic field, which operate only at the vicinity of the transformation temperature. Here transformation temperature means we are talking about, let us say, like a martensite austenite type of transformation, and if we apply a magnetic field very close to it, then we can shift this transformation temperature, we can stabilize one of the phase, whereas the second mechanism utilizes the redistribution of the simultaneously elastic and magnetic domain by an external field, which is called as MIR. Let us say the application of magnetic field reorient the martensite twin domains and so on. So, this is the second mechanism that we have discussed just a few minutes ago, and it is operative at temperature below the transformation temperature, means below the martensitic finish temperature we can get such a behavior. Now, we must explain those features, how really the actuation can occur by the application of a magnetic field in a material or ferromagnetic shape memory alloys. So, in this case let us say we take a such a ferromagnetic material, and we have a lattice. Here is the direction of A axis and this is the C axis, okay. And now we have applied a stress. So, this is already under stress. So, you can understand these are the fixed moment. So, we have a tensile stress that is acting on the body, and if now we apply a magnetic field, then due to the application of the magnetic field, the martensite that basically transform into austenite. Okay. So, the red color here is the austenite, and due to that we also changes and align the domains, and because of that there is a shortening of the length, because you see the A axis, the long axis along this direction and the short axis C is in this direction. So, there will be a length change, because C axis the direction of the magnetic moment was in this way. Okay. And so, now if we keep on increasing the magnetic field, so we can generate this strain which is the delta L. So, the net length was total length was L. So, the strain we develop by the delta L by L along the x axis. Okay. So, in short, let us say the magnetic shape memory effect we achieve for, let us say this was a typical 10 M martensite in a nickel manganese gallium actuator. The applying a tensile stress generate at a initial single crystalline state along the A axis, that being aligned along the x direction. So, A axis are aligned along the application of field, and for increasing the magnetic field along the x direction, the variance with the shorter C axis, these direction nucleate and grow in size a fully reoriented single crystalline state that is formed. So, the resultant length change correspond to a difference of the lattice constant, and m is the magnetic moment, here h is the magnetic field and sigma is the tensile stress. So, this is a typical magnetic field induced orientation or MIR type of relationship. So, magnetic induced orientation of the twin variants and so on. Now, we can also get, let us say, morphology of such a magnetic domain and martensitic structures in a nickel manganese gallium system. One can see that these are the typical twin structures, and here these are the boundary between the different twin lamellae. So, inside one of these twin lamellae we may have two different type of twins. So, these are the twin boundary. By application of the magnetic field, these twin 1 to twin 1 twin 2 type of growth occur, and by looking at the selected radial diffraction pattern from the brighter spot, you can clearly see 1, 2, 3, 4 and 5. So, this is a 5 m Martensite, modulated Martensite. So, along let us say the c axis, or let us say the transverse direction, the properties are different, means the magnetic moments are different, and it require the for a given application of the field, the moments that are generated along the transverse and longitudinal direction are also different. So, this is also another interesting behavior of such a magnetic shape memory alloys. Such a magnetic strain characteristic of a magnetic shape memory alloys linear actuator, we can also discuss this issue of how the domains are oriented with a application of a magnetic field. So, let us say I can start with a nickel manganese gallium alloy, and this is also a kept at a applied field of 0. So, there is no magnetic field. Now, I hold this particular strip or nickel manganese gallium strip with let us say 0.1 thickness, it is very thin, with a string, that is a copper nickel tensile string, which are kept at such a distance. And now, I put it here, means I apply some stress. So, this A axis now will be aligned along the tensile axis. So, I put a tension here. So, you can see the length of the spring has increased from this position to here. So, immediately the lattice will be also reoriented along the direction to accommodate the elastic strain. However, the magnetic moments are also aligned here, and so the spring has elongated actually, right. So, the spring get elongated, however, the length of the strip remain unchanged at a 0 applied field. Now, what I do now, the actuation really begin. Now, I apply a magnetic field. Okay. So, B here is the magnetic field. So, all these lattice here, they now reoriented along the applied magnetic field. So, C is the axis which should be aligned with that B, and so when the applied field is greater than 0, then there is a magnetic contraction, because C axis is the smallest axis and this position goes back. Now, I have much longer tensile spring. So, the load also has increased because of the application of the magnetic field. So, C axis align along B, causing a contraction. Now, if I withdraw the magnetic field now, in that case there is a simple mechanical elongation due to the application of this spring. So, again the magnetic domain are aligned in the opposite way, and the former state again comes back. So, this is a linear actuation in case of a ferromagnetic shape memory alloys. So, if you look at different preload. So, here whatever load we have applied, this is let us say a preload. So, this is the preload amount, let us say for 0.8, 1.4, 1.8 or 2.1. So, the net strain that one can generate could vary. So, from 0 we apply a preload, and then the strain again comes back due to the external field. So, initially the external field was 0 and then it comes back, whereas the green one almost reaches to something like 5% strain. So, this is a very large strain that we can produce, and beyond any kind of beyond the elastic limit of such a magnetically or induced strain that are recoverable strains. So, we can easily use this material as a actuator and already being used. The other one here, this is a heating and cooling require, which is used for micro switches, and in this case what we really do, we have a cantilever, and this cantilever is made of a ferromagnetic alloys, and for this cantilever we have a fixed substrate and stacked on a magnetic shape memory alloy that are freely movable cantilever at the end, and a magnet and a heat source. So, we have a magnet here and we have a heat source here. Okay. And these magnetic shape memory, these alloys, they are stacked heat source above the transformation temperature to a ferromagnetic austenite, causing the cantilever to bend out of the plane. So, here we are talking about MIM, means magnetically induced martensite to austenite transformation. So, ferromagnetic austenite that causing the cantilever to bend, because if we increase the temperature, then it goes to the austenite domain, and this austenite is a ferromagnetic in nature. So, immediately it will be attracted to the magnet, and so this connection will be disconnected, right. And so, again when let us say the temperature will be cooled down, then it will come down to the martensitic phase, which is a paramagnetic region, and so again it will be connected these 2 points. So, during heating and cooling we can use as a micro switch for ferromagnetic attraction as well as paramagnetic when or non-magnetic during cooling non-magnetic martensite or paramagnetic martensite, this magnetic attraction force will vanish, and due to the elastic reset force, then again it will come back to here. So, this process will go on. So, we can maintain or restore the initial undeflected state. So, in this way we can make micro switches that could be that is very much usable for using these shape memory alloys by considering this magnetically induced martensite to austenitic transformation. We can also use these particular magnetic induced transformation for control of fluid or glass flow. One should have a look here. This is a silicon substrate where the material is grown, and material means basically the alloy, that is a magnetic shape memory alloys, and this particular color region is the alloy. A higher magnified image with 100 micrometer that are shown here. So, this one is the alloy, and here this is the substrate actually. So, other version of one of such a switch is shown here. So, these are the micro valve, and here these are the connecting materials of these 2 different parts. Now, the mechanism of magnetic shape memory alloy coupling effect is due to the magnetic field induced reorientation of the martensite, temperature gradient induced structural transformation from martensite to austenite, and thermally induced ferro to para or antiferro or martensitic transition. So, means if we apply a magnetic field, then there will be a distortion in the lattice, and as well as it will simply assist to close the valve or to open the valve. So, the basic structure consists of a top cover where there is a need of a heat sink, and the shape memory alloy bridge micro actuator are shown here actually, and the below that the actuator carrier or spherical plunger, and there is a membrane with a valve housing, and there is a need of a hard magnet. So, finally assembling such a assemble part which we use for such a fluid flow control or gas flow control. So, also I believe that these are one of the very important aspect of ferromagnetic shape memory alloys for everyday's use. Now, these magnetic field induced strain or MFIS are due to the variation of the Martensite twin variants or a phase transition. In both way we can generate the strain, and the anisotropy factor, that is Ku, that I have discussed earlier with you in the last class, are lying here. So, this is the magnetization versus a magnetic field. So, if I apply the field, the Martensite which has initially a magnetic moment along this direction will be switched into the direction of the magnetic field, and with that switching we remove one of the twin variant due to the reorientation of the Martensite, or otherwise we can switch from a Martensite to austenite, or we can change the phase from Martensite to austenite by the application of the field, where we not only change the phase, but also we align the magnetic domain. So, these are the two different effect, one is the MIR and one is the MIM. So, field induced Martensite reorientation is occupying this region people have observed so far. However, here a minimum stress is required. So, in between let us say 1 to 10 megapascal stress, and the strain can achieve up to recoverable strain can be achieved up to 10%, right. So, this is a very high, since we can already calculate the work output by considering the stress and strain. So, these are the lines that are let us say 2 kilojoule per meter cube, 5 kilojoule per meter cube. So, as we go into this right hand side direction, we can get a higher work output of this, right. And on the other hand, let us say the field induced reversible phase transformation that are present, which are occupying this particular region, but the best idea will be to go to this side actually, right. But so far there is a magnetic field induced one way phase transformation has been observed, which require why this is one way, because it requires change of temperature or the stress in order to recover the strain. So, if we withdraw the magnetic field, then it does not recover the strain actually. This is a one way phase transition. Okay. So, but the target is to get a reversible phase transformation in this domain, so that we can get the maximum work output of 2000 kilojoule per meter cube. Okay. But people are developing these alloys day by day, and so many interesting alloys or material could be developed using these kind of half or full Heusler type of compound, and switching between austenite to Martensite and to develop these ferromagnetic shape memory alloy. With this I stop today's discussion, and we will continue with the discussion of some of the other functional behavior of these advanced functional alloys in the next class. Thank you very much.